since I'm not here today, I'm gonna run out the last little bit of notes that we were supposed to do in class today that you all aren't gonna get to see from me. So the last couple of proofs, you can pause this so you can copy it down if you're watching this as a class. But we are given that angle BAC is congruent to angle DEC. So BAC is congruent to angle DEC. So mark that on your picture. First statement in the proof is always given. We don't get anything else from that. So we move on to the next one. C is the midpoint of AE. So, vocabulary word. Midpoint means what? That's one of those chop in half words. And if C is the midpoint, it's the absolute dead center of that segment right there. So AE is this segment. C is the midpoint. That means this segment is chopped in half. So that part has to be equal to that part. So if you remember from the other geometric proofs that we did, that if we had a vocabulary word, the next thing that we had to do was to define that word. So for number 3, we need to put what that just told us. We need to say AC, the segment, is congruent to segment CE. And the reason that we knew that was because of that vocabulary word that we were given. So for number 3, definition of midpoint. So, since we're there, we've got to find something else about this picture that we can pull out of there that we know because we've used all of our givens up. C is the midpoint of AE. It did not tell us it's the midpoint of BD, so we've got to pull something else from somewhere. It doesn't have any shared sides. We don't know anything about angle BD. We don't know about AB. We don't know about DE, how those two relate, but we do have that crisscross right there. And anytime we have a crisscross, we have vertical angles. And vertical angles are always going to be congruent to each other. So right here at angle C, in each of those triangles, I know that those two angles have to be congruent to each other because they're vertical angles. So that's not an assumption. That's something that happens every time. When you have two lines that intersect, you always end up with vertical angles. So, or completely intersect, I guess I should say. So for number 4, we can't just say angle C is congruent to angle C because there's several angle C's up there. So we have to be specific. We're going to say angle BCA is congruent to angle DCE but we knew that because they were vertical angles. So we're going to say definition of vertical angles. Now, a question I got asked this morning that was a great question was, Ms. Lezeski, what you wrote down for number 4 does not match what you have up here for the proof. Because we have angle BCA and angle DCE. Up here you have triangle ACB and triangle ECD. And the congruency statement has to match. Like the corresponding parts have to go together. But remember what we're doing. Down here for number 4, we're just trying to say that angle C is congruent to angle C. We're not trying to say that the two triangles are congruent yet. So where up here, we're having to make sure that the parts correspond. Down here with the angle, we just have to make sure that the vertex is in the middle. So it doesn't matter that this doesn't say exactly that. Even though C is in the middle up here too, which is okay, that's what we need because C is obviously going to correspond, they're equal. It doesn't have to be the same thing as it says right there in the proof. So keep that in mind. Now, When you go on to prove the triangles though, remember what we were shooting for. We were shooting for one of those 5 postulates. Side, 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 angle, side, angle, angle, side, or that hypotenuse leg. So, looking at what we have to check the pattern and see what we've got going on. So if you look at just one of the triangles, we've got angle, side, angle, side, angle. It's that included side. So our postulate is the angle, side, angle congruency postulate, because we got the same stuff in both triangles. Our statement is going to be that congruency statement that we're given up there, and it has to say exactly what it says there. So triangle ACB is congruent to triangle ECD. So you can pause that if you need to. That's what our proof is going to look like for that angle, side, angle. Now, moving on to this one. This one's a little bit more complicated. Mostly because the picture is kind of wild. First statement in proof, always given. So angle DAC is congruent to angle BEC. And we were also given that DC is congruent to BC. Both given. So, marking our picture, DAC is this angle right here. BEC is this angle right here. So, if I were here live in person, I would ask you right now, how many triangles are in this picture? And I would get the answers 2, 3, 4, 5. The answer is 4. You've got these 2 little triangles right here. You've got this triangle, ADC, and you've got this triangle, EBC. Now, lazy math teachers like to create pictures like this and then have you answer multiple questions about it. So you really have to pay attention at what 2 triangles we're asking you to focus on. So I'm going to look at my congruency statement. ACD is this big triangle here. And I'm comparing it to ECD, that other big triangle that I highlighted just a minute ago. So those are the ones we're focusing on, not those little bitty ones that we have over there to the side. So keep that in mind. So that was the first given. The other thing that we know is that DC is congruent to BC. So I know that this piece here and this piece here are congruent to each other. Now I highlighted those in blue because notice it's not the entire side. It's not the entire segment. CD is the entire side of that triangle there. And BC is the entire side of that triangle right there. But it kind of makes your eyes cross a little bit when you look at this because we want that to be part of a triangle that is congruent, a side that's congruent, but it's not. CE is a side of BEC, but that's not part that's congruent. So finding the next thing that we had to go here kind of made my eyes cross a little bit. What I had to do, because my eyes kept going here to these vertical angles, but those vertical angles don't have anything to do with the 2 triangles that I'm trying to prove. So I had to go in and separate them. So I had to say, okay, what am I working with here? I've got angle ADC I know A and DC have been marked. And then I've got BEC and angle E and BC have been marked. And I had to find something else in those two triangles that I could pull out of that picture to use to prove one of those postulates. So I've got an angle and a side, so I need at least one more angle or one more side to be able to do that. So looking at what we have, these vertical angles that I mentioned before, because that's what my eyes jump to, and that's what every other class has said too. But those vertical angles are like right here. Like in the middle, not middle, that's a terrible word, I shouldn't have said that, but somewhere along that side that has nothing to do with any of the angles in those two triangles that I'm trying to prove. So they're not helpful at all. I don't know anything about the other sides, but what I do know is that both of those triangles share angle C. Angle C has one vertex and it's made up of two sides. There's not another segment in there or ray or anything to split that again. So that angle, just like a shared side, you know, we've had to use those triangles and share a side. That side is not going to change sizes when you go from one side to the other of that picture. Angle C is not going to change sizes either. So we can say that angle C is congruent to itself. And that gives us one of those postulates. So we can say for number 3, angle C is congruent to angle C. And we don't have to name it any kind of crazy way with extra letters up there because angle C is not changing. And what that also allows us to do is to use the reflexive property to cover that. And then look what it did. We have angle, angle, and a non-included side. Angle, angle, and the same non-included side. And I can see it when I have my picture separated. It's really hard to see it for me on the one that my picture is together. It just looks too jumbled on the one where it's together. But I have proven my two triangles. By angle, angle side, whoops, congruency postulate, and we're good to go there. So this was the second section that we were supposed to cover. And then I want to go and talk about a couple things from the third section. So if you go to page 321, there's a couple postulates on there, and this is the section that the HL postulate came out of. Remember, the HL postulate is the one that takes the place of the donkey postulate, that angle side-side postulate that doesn't actually exist. The state of Tennessee does not test you over these two. So if you look on page 321, there's these two postulates. The first one they call the leg-leg postulate because these are specific to right triangles. But these are not in our standards for Tennessee. These might be standards in other states, but they're not in our state. So if you look at the picture, I only drew one triangle of the pair, but if you look at the picture, what postulate does that look like that I've already taught you? Side, angle,